without really leaving the frame of initial Flory-Huggins approach is to consider the polymer blends. The polymer blend is a mixture, is a solution of a very high molecular weight polymer in a high molecular weight solvent. I will always consider solvent as having lower or the same molecular weight as a polymer. Now the difference to what we have considered in our lecture yesterday is really minor. If we know, and we learned how to do it, if we know how to construct the entropy of a mixture of different objects, we can easily construct an entropy of the mixture of two polymers, one of which occupies the overall fraction phi of the sides, so having essentially concentration proportional to phi, and another one occupying the fraction 1 minus phi of the sides. So the only thing here is that when approximating these entropic contributions by the translational entropies, like we already discussed it, you only take into account the positions of the beginning of the polymer. The rest gives you a constant contribution. And therefore, our approximation for the entropy will be like this. Now, this existence of ln phi divided by Na, it's not very interesting, because we will see that these terms, which are linear in concentrations, they do not give any physical or physically important, let's say, contributions, but the rest is important. And let's have a look what happens. So now I build the free energy according to our usual approximation. So I assume here in the term with internal energy, this quadratic kind of interaction or bilinear kind of interaction, which means that I assume that the monomers in the polymers are arranged at random and somehow well mixed. This is an approximation. And here I took these terms of the translational entropies, fully neglecting the contributions of the internal degrees of freedom of the molecules. And you know it's an approximation, but we have seen that it's okay. So let's play with this in order to try to get some physics out of it. Now, if I have this internal energy, I can calculate its derivative in phi, and then its second derivative in phi, and then putting the second derivative equal to 0, I get the spinodal. And since the calculations are identical to what we have done, I can immediately put down the equation for the spinodal, and this looks like this. So the only difference is that in our case, yesterday, one of these ends was essentially 1. So NB was 1. Now I can take a derivative of phi with respect to phi to find the lowest point of this spinodal, which is a critical point. And I get the position of the critical point and the critical value of the Flory-Huggins parameter. So what we see is that if both the molecular weight of the polymer and the molecular weight of the solvent, or the polymerization degree of the polymer, polymerization degree of the solvent, are large enough. So I have here large numbers, and I have the polymer much longer than the solvent. Let's look what happens with high C. So here only this guy survives, and I get here Na divided by twice Na and B. So high C in such solution will be equal to 1 divided by 2 NB, which means that the critical point approaches the thermal line, he equal to 0. And this means that the mixing could take place practically after crossing this 0 line, which means here, or approaching this 0 line, already at very low temperatures. This means essentially that if you have the corresponding concentrations, the two long polymers, if the monomers really repel each other, they will always demix. Now, what I would also like to do is, I will need it a little bit later. Let's have a look what happens if phi is small. So you have now a solution of a small amount of long polymer in a polymeric or oligomeric solvent, but not a solvent consisting of small molecules which you can consider solid entities. So here something happened when I was editing the file, doesn't matter. And here I will simply take the Taylor series of this guy, assuming phi small. So this is small, this is small. With the logarithm I can do nothing, but here I can safely expand. And what I obtain is such an expression where I have a term linear in phi, containing phi, where I have a term quadratic in phi, where I have a term cubic in phi, which stems from the expansion of this expression here. And I have the standard term phi ln phi, with which I can do nothing, or I do nothing. Now, let us have a look at what happens. For example, let us try to repeat our calculations which we performed, for example, when considering osmotic pressure of polymers in such situations. I will explain why do I do this. Now, let me just a second go to one of the previous lectures, namely, just a second, namely to the one where I considered the osmotic pressure. This was our expression for the osmotic pressure. It was derivative over phi of n monomers, the total number of monomers in my system, the total number of monomers in my longer polymer, if I'm considering the osmotic pressure of these longer polymers, divided by phi times f of phi, where f of phi is this form of the free energy, which in the free energy is multiplied by kBT. So just remember this formula, f of phi divided by phi, and then I take the derivative of it. And now I come back to the lecture here. So I have now this, what is in the square brackets, is my small f of phi. Okay, maybe within zeros there, but it doesn't matter. And if I am calculating whatever responses, which means whatever derivatives of this f with respect to anything, this anything always comes via phi. We have seen it in the last lecture, where also x came essentially via phi there. And if you take f of phi divided by phi, the linear term gives you a constant. And if you differentiate, it simply disappears. This means that the linear term is not responsible for any physical properties which could be interesting for us. This is the only statement. It is important in some cases, but if we are calculating, I don't know, pressures, whatever, it simply disappears. So it starts here from the second term, which is important. Here we see this phase separation, so everything starts to happen, the change of the regime starts to happen in I equal to 1 divided by 2nb. This is this. This defines me the critical point. And then I have this term with phi cube, which will play some role afterwards. But the prefactor in front of this term can be made small if I consider high molecular weight solvent. And this is an important observation which will play some role in what we will discuss at the end of the lecture. Now, this guy, the prefactor of the quadratic term, I can put down as high minus high C, because I have seen that this is essentially high C. And now we can consider many problems with these polymer blends, which means solutions in high molecular weight solvent, which are similar to the standard Flory-Hagens problems for low molecular weight solvent. There is, you will get the corresponding homework, and there is another thing which you will get as a homework, which is the following. The case of a symmetric blend with the same molecular weight of both components, which is however large, is essentially parallel to the binary alloy, where it is the same, but n is equal to unity. It's really the simplest case for considering the phase separation. And in this case, you can easily calculate, and this you will get as a homework. There will be also an explanation of how to do this. You will calculate both the binodal and the spinodal of the system. So this is, the upper curve is, as always, a spinodal, and the lower curve is a binodal. I plotted them for n equal to 100, and you see that here, contrary to this low molecular weight, where the spinodal was not as flat, they both are flat, both touch at the critical point, which is here exactly at 0.5, and you can easily calculate both, and it's a good training. So if you put in our formulas here, NA equal to NB, and both large, then you have here 4 times, you have twice square root of n squared 4 times. There is something wrong here. 4 times an a, and here you have twice an a and b. So what essentially what you get here is I c equal to 2. I have to check, or it is something wrong. Here you get 1/2, which is correct. I will have to check. So high of phi reads like this for the binodal, not bimodal. And the spinodal is like this, and they are symmetric. So you get 1/2, and at phi 1/2 you get here 2, 2. It must be high equal to 2. There's something wrong with the scales on the picture. But this I do not like very much. I will check. We will check it now. Let me go up to the very end. You will also get it in the homework. So let me check what went wrong. Now, let me do the calculations, because now I am somehow unquiet. So let me stop this. Let me open this, and let me share the screen from the tablet. So we start from our expression high equal to 1/2 1 divided. Now I call n a. I consider the symmetric case equal to n b equal to n. Then it will be 1/2n, 1/phi plus 1/1 minus phi. Here it is clear where the minimum is, because the minimum can only be at phi equal to 1/2 because of the symmetry. I know that there is a minimum, so this will be high equal to 1 divided by 2n. And here I have, I know whether, and here I have 1/2, 2 plus 2, 4, which means 2 divided by n. And this is correct because somehow I got afraid too early. If I now put high C, this my expression, which I used to have high C n A 1/2 plus nb 1/2 squared twice na nb, and both are the same. This will be 2 square root of n squared 2n squared. It's 2 divided by n. This is correct. Okay. Sorry for disturbing you with these stupid things. And now let me close the screen and share here my screen with you once again. Mhm. Stop. This is not. Don't save. Is this what I wanted? No. No, no, no. Just give me, stop. Just give me a second. I'm now in lecture 10. And now let me go back to Zoom and share the screen with you. Here. So then for the binary mixture, I get here this 2 divided by n as the position. I can easily get the equation for the binodal, which is normally hard to get because you have 2 minima of f of phi. You have 2 minima of this function, which are symmetric. If NA is equal to NB, the minima are symmetric. And in order to find the binodal, you need to find a line which is tangent to this function at the 2 points, at the 2 minima. And for the case, if you remember my picture from the previous lecture, lecture 9, let me come back here. Yes, this was this f of phi, doesn't matter. So this was red, and here you have to find a solution of the 2 equations so that the derivatives here are equal and the derivatives lay on and the tangents make a single straight line. But if this f is symmetric, then essentially the whole curve looks, let me just a second, let me just comment on this here. Now, somehow I do not see my screen. Just let me do it again, because there is a problem with continuous problem with connection. Okay, now it seems to work. So now this line, which was complicated, which looked complicated, f of phi, in the case of an asymmetric mixture, now it is absolutely symmetric. So that this line, this common tangent, it is symmetric. It's not very symmetric in my picture, but somehow it did not again show you the full screen. Okay. I will do it once again. I hope it works. Just a second. Once again. Now you see my figure here. You don't see anything yet, but I hope it will come. Otherwise, I will turn to whiteboard. Okay. Let me turn to the whiteboard. Okay. Now I even cannot stop it. This is a problem. Wonderful. So I stopped it. I turned to the whiteboard. Just a second. So what we had when we discussed how to find a binodal, we had to draw a picture, phi, f of phi, and this could be phi, and it has two inflection points, and then we had to find a line which is a common tangent to this curve f of phi in two different points. And this, if we do it algebraically, this implies solving of a system of two equations, which are not always easy to solve. But for a symmetric blend, this f of phi, just as for any essentially binary solution of symmetric elements, this f of phi is a symmetric function because it is essentially, if it has a maximum or a minimum, this is at 1/2, because phi and 1 minus phi simply correspond to renaming of A into B and vice versa. And if you have a symmetric function, and this symmetric function has a minimum or whatever, then the two extrema are at the same height. So this is the common tangent then. So therefore, this variant of the theory is easily solvable. And now we go back. And then we can easily obtain the result, which you will obtain in the homework, which is this. And then one can plot it and one sees what happens, and one can also see that the spinodal and binodal touch in the critical point and many other things. And these are really simple. Now, there is another interesting thing, quite an important thing, essentially, to discuss. And this is considering the block copolymers. Here, I will only tell a story without making any calculations. I can explain how one can do these calculations, but again, let's qualitatively discuss what happens or what might happen. So now imagine that A and B are not two different polymer molecules, but two different parts of the same molecule. So A and B are connected to each other. And here I have a binary block copolymer. Now, if this connection would be cut, I would have the previous situation of a polymer blend. Now, interesting is what happens if in such a polymer blend, the constituents would like to demix. Because it means that this A or B part would like to demix from this. But now they are not able to demix and to create separate phases because they are connected together. So essentially, you cannot build two thermodynamical phases, but you can build a structure within a single phase. So what you get here depends on the relative size of the components. So now, in the demixed situation, A's would like to be together and B's would like to be together. And they would prefer to build such a structure in which the total free energy is minimized, which means in which, in some extent, there is the smallest surface of phase separation, the smallest surface around which A's and B's can touch, because there the internal energy increases. And the situation that appears depends really on the sizes, on the polymer, on the size of the number of monomers in different parts of the molecule. If the A part is short, then essentially what you have A's together and B's showing to the outside. So you get the micelles. I have drawn here in the blue circle only the part of the single molecule, but essentially what happens is that A's from different molecules would like to sit into these droplets, and so to say the tails are outside. And then the tails feel only the tails, and the heads feel only the heads. Now, if LA is smaller than LB, but not much smaller, then the typical situation will be forming the cylinders. In these cylinders, the A's are again together and the B's are outside. And the cylinders can essentially have a complex topology. Not that there are like columns, they can also somehow undulate. It's a complicated stuff. So what you have here, you have enough translational entropy of translating the droplets. But if these guys are long, you get, by forming the cylinders, so to say, less loss in the translational entropy than you have, so to say, the decrease in the interaction energy. Once again, say that the calculations are tricky, experiments are nice, and I simply tell the story about what happens without giving correct explanations. And if they are of a similar length, then essentially you have a structure of alternating domains of A's and B's. So they do not, since A and B cannot separate, they do not form macroscopic phases. Because this guy is essentially, or this guy is of the size of the length, essentially square root of the length of the corresponding part. Because what you have here is something like a melt of the heads, so to say, and here you have something like a melt of the tails. But this is an important and interesting situation, and it was, and it still is, under investigation, under extensive investigation, because there are also materials which are built like this. Okay, so now we finished with the first part of this lecture, and we can go to the second part. And now we will discuss the behavior of single molecules in a dilute solution. Essentially, we will return to our Flory discussion of a self-avoiding chain and have a look. We only perform this situation with this discussion in the case of a thermal solvent. And let's have a look what happens with the molecules in a good solvent, in a poor solvent, or on the transition when high is equal or around 1/2 in a dilute solution where you have the transition from good to poor solvent or back. So this is now our next topic. So if we look at our let me draw a picture. If we look at our phase diagram, high, phi, 1/2. And here was our spinodal, and here is our binodal. Here I have good solvent, up to this line. This line is called theta solvent. This is when I is exactly 1/2. And here I have poor solvent. But we have to know that essentially the quality of solvent is defined by the temperature. And now I am looking here at small phi, where I am in the dilute solution. Why is it interesting? Because first, it's interesting in biological applications. And second, it's also interesting from the point of view of physics, because we see something which happens with single molecules. And this something is very non-trivial. Now, let us try to build a theory of these single molecules, which means of molecules in a dilute solution, in the case, not in the case, but already having the machinery of a Flory-like approach. And I again start with my molecule, but now I do the following. All my molecules are all my monomers are in the back. I said that essentially a molecule, just like in the Flory description, which we considered, I will consider the translational entropy of the monomers. But instead of translational entropy of the polymer, now I have fixed a polymer. I'm sitting at its beginning. It doesn't have the translational entropy. I take its internal entropy. And this internal entropy I approximate by the internal entropy of the ideal chain. This is here. So what I have now here from the Flory-Huggins, I have the interaction between the monomers and the solvent molecules, which is characterized by the Flory-Huggins parameter. This is exactly the same what I used to have in the Flory-Huggins. I have the translational entropy of the monomers, which is exactly the same as I used to have in Flory-Huggins. And essentially it stems from the lattice gas model. And instead of considering in my theory the instead of considering in my theory the translational entropy of many molecules, I say I am now within one molecule and I'm considering the change in the entropy of the molecule due to change of its internal conformation. This is exactly the term of the type which I have fully neglected when I had many molecules. So is the approach clear? This is the question. Because I have a feeling I am speaking in front of an empty room.
Initially, they said
Just, I didn't get... Do I have to explain something in more details, or I can go further?
For me, it's okay. You can keep going.
Good. So now this is, once again, interaction, translational entropy of the molecules, change of the entropy of a molecule, of a single molecule. I will then work on this term, but first let me have a look at what happens if I assume this form, whether I can reproduce the cases I already know. Now let me start with this form and look, here I have R, here I have phi. What is phi? The concentration of monomers. This is, I am looking at this, so to say, back. Yes, with the monomers. And phi is the total concentration of the monomers within a bag, a ball of radius r. So I express this phi via Na cube divided by r cube. So I have is it clear what happens here?
For me, yes. Don't know about the others.
I have a problem that for me, not really, because, okay, this is, I used to have, so phi, let's have a look what phi is. Phi is a cube divided by r cube. So here I had to have phi to the power of 6. Here I have to have phi to the power of 9. But, okay. And there is here n0. And n0, look at these two equations. Let me check it for myself. I remove this figure. So what I had was f is equal to something. I neglect this something, n0 kbt. And then I had this 1 minus phi high, or 1 high minus 1 phi. So I simply copy the formula because 1 minus high phi. Then I have the plus 1/2 minus phi squared plus 1/6. This we can remove. Phi cube plus blah blah. And now I say phi is equal to n. N is now the number of monomers, a cube divided by r cube. And I say that n0 is r cube divided by a cube, which I didn't put down there. So because I have now my polymer, and I look at this lattice model, and I'm looking at all sides which are inside of this ball. And this is exactly the number. So now I substitute this into this equation. So I get kBt r cube divided by a cube. Then I get here 1 minus phi, this guy, n a cube divided by r cube, plus 1/2 minus phi, now this guy squared, n a cube divided by r cube squared, plus blah, 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 plus the rest. And now I see what happens. First, this guy here cancels. So there is n coming to the outside instead of n0. And now in all the rest, 1 power of this cancels. So here I have again n a cube divided by a cube, n comes to the outside. And then in the last term, again, 1 power is lower, but there is still n there. So this is the expression. Now let's have a look what happens. Now let me minimize this term. First, I can neglect this, because if the chain is swollen, it is large. And this guy is much smaller than this guy. It's 1 divided by r to the power of -3, this r to the power of -6. So I take only this term, and this has to compensate. Now I have to get the minimum, and this I forget at the beginning. So now I differentiate this guy with respect to r, and I obtain a solution. And this is my solution. And now I solve this equation, and what I get is r is something. Here I have this something in the term of the type of 2/3 to some power. It doesn't matter, but essentially I do not know correct prefactor here. So this means that I do not have this prefactor, some constant. Then I have this 1/2 minus phi to the power of 1/5, because it was r to the power of 5. And then I have a n to the power of 3/5. So what do I see here is the following. If I look at high below 1/2, if this guy is positive, then I get the dependence r going as n to the power of 3/5. This is Flory. And this Flory is okay not only for the case of the athermal solvent, which means not only for the case of genuine self-avoiding variant we have considered up to now, it is okay in the whole domain of good solvents. And the quality of solvent, which is sitting in high, is essentially not very important, not only for the behavior as a total, but also for a prefactor, because the dependence on this high is the fifth root of 1 minus high in 1 minus high, so to say, 1/2 minus high, which means, you know, if 1/2 minus high is 10 to the power of 200, I get hardly a factor of 2 in the difference of the radii. So in the whole domain of good solvents, this variant of the theory predicts that I have something which behaves like a self-avoiding walk, like this self-avoiding chain or excluded volume chain, and it hardly depends on the solvent quality as long as the solvent is good. But there is a difference when high is very close to 1/2, because then this is 0. And R equal to 0 is a nonsense, because there is still a repulsion between the monomers, and they cannot collapse into a point. So at 1/2 or around 1/2, something happens. And just like the genuine Flory-Huggins needed for consideration of phase separation, we need here for consideration of some other physical effects which explain us what does happen indeed. So now let us have a look what might happen. Let us go with high from below, when this is positive, and I can take the fifth root of this, and approaching R. This guy will decrease and decrease and decrease. Of course, it cannot decrease more than n to na cube. It simply means that this dependence of n is what breaks down. Now, let us do the following approximation. Look, here we used the approximation for the entropy or excess entropy in a chain which is pooled at the ends. But we also know from the consideration of the behavior of a chain in a pore that the entropy of the chain will grow if you squeeze it. So there must be a term which describes the change of the entropy when R gets smaller than the unperturbed length of a simple chain. And this is something I have already spoken before. So what I do here, I interpolate between the two situations. I take a function which safely reproduces the existence of the excess entropy when the chain gets larger than a simple chain, and also when chain is smaller than a simple chain. It has correct dimensional dependencies. KB is not, T is not there, sorry, because this is the entropy, this is not the free energy. I simply copied it from here and repeated it. It was a mistake, so T is not there. And this is for a chain pulled at the ends, and this is for a chain squeezed in the pore. I'm not quite sure that for R of the order of R0, the prefactor here is correct. Maybe they're mixed slightly differently. But the asymptotic behaviors of very large R and of very small r, in which cases both the entropy grows, it's kind of this parabolic-like behavior, is reproduced correctly. Now, is the point clear? Because it's the only important point. Then some wonders will come, but this is the only important point here. And this T is absent. Sorry. Although I reread it on the weekend, you can never see all mistakes. Now I'm using this formula in combination with my Flory-Huggins-like approach. So I say this is the entropy or the free energy of the bag, and this is the free energy of what is inside the bag. This is the internal energy, the interaction, and these are the higher corrections here, which come from the translational entropy of the monomers, which come from here. And now I have this kind of a total energy. Now I introduce the swelling parameter. This I do only on the reason the swelling coefficient. This I do only on the reason of mathematical convenience, because I will get an equation which I cannot solve anyhow, but I can at least analyze it when introducing such a parameter. And this is R divided by R0. This was a 0, this was a 0. And I express everything via this swelling parameter. And when I express everything as a function of this swelling parameter only, what I get is the free energy of my system, of my chain with monomers inside, as a function of this swelling parameter, which, except for number parameters here, okay, I don't know the exact numbers here, but I know this number here, for example, and the size of the molecule, the n, is only on one place. It's here. Now I have an equation. And this is written for the low molecular weight solvent. And if I have a high molecular weight solvent, oligomeric solvent, and what I never showed you, if I have a polymer which is stiff, because in this case it's harder to correctly choose the lattice, and I never wanted to go into detail. And if I have the high molecular weight solvent, I have here 1 divided by n, so 1 minus 5 by n, ln 1 minus 5 by n. Instead of this 1/6, I will get 1 over 6n, something like this. It's even written here. So now I have an equation, and this is an equation where I see the powers from -6 to 2, many orders of magnitude. Now, let me try to analyze this equation. I want to minimize the free energy because the conformation my chain will attain under different conditions corresponds to the minimum of the free energy of the chain. And here it can minimize its free energy by getting larger or smaller, by either putting inside more and more solvent and blowing up, or by squeezing the solvent out and getting smaller. Now I differentiate this guy with respect to alpha and put the derivative equal to 0. Again, I have here two numbers. This number I know. This number I really don't know, but I know it's of the order of unity. What else? And this is qualitative anyhow. And now what I can also do, I can introduce two parameters. There are two parameters, essentially two free parameters, which I call x and y. X is this guy divided by c, or 2c. So I remove this. And y is this b3 divided by 2c. And c is of the order of 1. B depends on the molecular weight of the solvent. X depends on high. The sign of x depends on high. Then there is square root of n here. It depends on the degree of polymerization. And high may change sign. Sorry, x may change sign in dependence on whether my high is above 1/2 or below 1/2. Now, this is now my equation, which I express via my parameters x and y. And now let's have a look what happens in a good solvent, in a theta solvent, and theta solvent is x equal to 0, high equal to 1/2, and in the poor solvent where x is smaller than 0. Now, because I have a long polymer, when I play a little bit with high, x immediately and either shoots up or, so to say, shoots down. So x in interesting situations, except for the situations extremely close to the theta point, is either very large or very, it's always very large in its absolute value, but either positive or negative. So now let us take this x very large and positive. So I have here something very large and positive. Now let's have a look what happens. Alpha is larger than 0 because the end-to-end length of a chain cannot get negative. So alpha is positive. Here is something large and positive, therefore this is large and positive, and this is then small compared to this guy, and this is very small. So then I have alpha of the order of the 5th root of x. And this means this guy here. So if I put now express r via alpha, r is r0 times alpha, r0 times alpha, and then these powers 1/2 plus 1/10 give me exactly this 3/5. And here I have 1/2 minus x 1/5. So this reproduces the result which I got before when considering the swelling of the chain. This is exactly what we already have had before. Now, let us have a look what happens in a poor solvent. It's poor. It's officially called a poor solvent. It's not a nice expression bad. Don't use it. I don't know why I typed bad, but it's a poor solvent. Now let's have a look what happens if x here is large and negative. I put there much smaller than 0, but it means large and negative. This is large. Now, again, if I look at this equation, this is large and negative. Alpha cannot get negative. Alpha is positive. So if X is large and negative, then the only way to compensate is to have this part negative. Now let's have a look, or maybe this part negative. What does it mean? So can I get somehow this negative? Not really. I can get this large and negative, in which I take now, this is negative, this will be positive, this will be around 0. Alpha is very small. Alpha minus 3 is extremely large. Alpha is by itself positive. Compensates X, and the both guys are small. Now I have said too many words. Is it clear how does this situation come? Is it clear or not? I have to try to explain it in different words.
I'm a bit lost.
Yeah, exactly. Me too.
Okay. So now look. When you are lost, tell me. Now look what I'm doing. Let me put now X, it is, I will put it minus absolute value of X. It's huge and negative, is equal to, let me put everything on one side. Alpha 5 minus alpha minus y alpha minus 3. Alpha is positive, is always positive, because the size of the chain cannot get negative. Y is a number, 1/6, or maybe smaller, 1 divided by 6 and solvent, positive number. This is huge and negative. If I take this huge and negative, this means that alpha is negative, which is forbidden. So the only thing to have something huge and negative in the right-hand side of this equation is to take alpha small and positive. Then alpha to the power of minus 3 will be huge, and because there is minus in front, this will be huge and negative. If it is huge and negative, then this guy is small, and this guy is even smaller. So I can forget the both. And the solution will behave as a solution of an equation, X is equal to y alpha to the power of minus 3. And now let me analyze how does this solution behave. Now I have alpha goes as y divided by x to the power of 1/3. Wonderful. Now I put this alpha here, which means to get the radius, I have to multiply R0 by alpha. This is R0. This is my alpha. And this is what I get. So I get high minus 1/2, because it was minus x, now absolute value of x, to the power of minus 1/3, a n to the power of 1/3. Now what does it mean? What is r going as a n to the power of 1/3? This means essentially that r cube goes as a cube n. This means that I am close to the close packing of the monomers. So what my chain now does, it as a single chain tries to phase separate from the rest and to build a ball. And this is called a globular. So it tries to build a ball and to have as little contacts with the solvent molecules as possible. Not really as little as possible, because there is here this prefactor, and when high comes close to 1/2, it grows, the radius grows, because exactly at 1/2, it's also clear what happens. Now let us have a look what happens exactly at 1/2. Where is my equation? X is equal to 0. There is no parameter here. Alpha is of the order of unity. It's a number. It depends on y, but it's a number. And then R is of the order of R0. The chain behaves as an ideal chain. So we have the transition between, in a good solvent, deep on my phase diagram, negative highs or small positive highs, practically up to a domain of the thickness of the order of square root of n around 1/2, around high equal to 1/2. You have good solvent and the chain is swollen and behaves as a self-avoiding chain. Then above, at high, which are larger than 1/2 plus something of the order of square root of n, you are in the domain of a good solvent and the chain behaves as a self-avoiding chain. And if you are in this narrow band close to high equal to 1/2, the chain behaves practically as an ideal chain. Therefore, essentially, if you want to make experiments with ideal chains, you simply make these experiments close to the theta point. You even don't have, if you want to have that in the dilute solution, not in the melt. In the melt, the chains are also ideal. But in a dilute solution, you come with your temperature to a theta point and you have your ideal chains there. You can test the theories for ideal chains, which are simpler. And then you can also somehow understand whether your ground theory, so to say, is okay or not before you are doing some approximations in the direction of self-avoidance. Now let us have a look at how the transition between this swollen chain and this globular, which is essentially a droplet, a chain which squeezes out all the solvent, or practically all the solvent. So the swollen chain soaks the solvent and the globular squeezes it out. How does this transition take place? And for this, I again look at this function and I plot now essentially the following. I introduce, where do I do it? Just a second. Yeah. I divide everything by, so look at my equation, and I will explain what I'm doing. I put everything which contains alpha on one side and let this function be equal to x on another side. So a5 minus alpha 5 minus alpha minus y alpha to the power of -3 is equal to x. And I call this function alpha 5 minus alpha minus y alpha to the power of -3 f of x. And now what I'm doing, x is essentially a number times 1/2 minus high times square root of n. It depends on n, it depends on high. And now I am looking for the solution of the equation f of x is equal to of alpha is equal to x. And now I see that the functions f come in two types. I will analyze it. This is the cubical root of f, because otherwise you don't see the details, and here you augment the details. But essentially it is f. And the f's come in two types. This f, independence on y. There are monotonic f's, and there are f's with a minimum and a maximum. Now, this is my function f. This is my function f. And to say whether the function is monotonic, like, where is my picture? Here. Like this blue one, this is monotonic, or has a maximum and a minimum like the red one, I have to take a derivative of this function. And the derivative is here. And then to find where the minimum and the maximum is, I have to solve an equation, this equation. And this is a nice equation, a simple equation, because it's essentially a quadratic equation. If I multiply this times alpha to the power of 4, and then denote alpha to the power of 4 by z, this is what I get. And about a quadratic equation and its real roots, I know that a quadratic equation either has two real roots or none. This means that if it doesn't have a real root, the function is monotonic, its derivative never changes the sign, and if it does have real roots, there is a minimum and a maximum, and the derivative does change the sign. Now, this means that independence on y, there are two different regimes. Now, what is this y at which the transition takes place? This is 1/60. And now let me return to a question of what is my y. My y was B3 divided by 2c. I don't know what c is, but c was of the order of 1. B3 is 1/6 for the low molecular weight solvent, and it is 1 divided by 6 and s for an oligomeric or polymeric solvent, for larger solvent molecules. This means that if for low molecular weight solvent, B3 divided by C is larger than 1/60, and I know that it is because I know the experimental data, the molecules can form the molecule collapse. Now I know that I will definitely have, for small y's, for large molecular weight solvent, I can definitely come into this regime. And now let me look at this graph once again and discuss how does this transition between a swollen polymer chain, between a coil and a globula, takes place when I cross the critical temperature, when I cross the theta line, at which phi is equal to 1/2. If this function is monotonic, then imagine I start here, and this is alpha larger than 1, which means I start in a good solvent domain. My chain is swollen. And then I go with x down to the domain of poor solvent. Here now I have some x, but at each x I have exactly one root, which means one size of the molecule which corresponds to the corresponding value of high. N is fixed. This is x, and x was proportional to 1/2 minus high times square root of n. Don't forget. So here I have a gradual crossover. It's called a crossover. It's a slow change of regime. I cross from the regime of a swollen chain over to the regime of a globular, of a confined, squeezed chain. Now let's have a look what happens if my y is small and I am in this regime where I have two extrema. And now let me start here and have a look what happens. So I start here. This is a regime of a good solvent. And I go along this curve when I take x smaller and smaller, which means when I lower temperature. I come here. Now what will happen here if I lower temperature further? Who can tell me? Ladies and gentlemen, what do you think? What will happen with the chain? No thoughts. It's essentially very similar to what happens at the spinodal. Chat? I have no idea. Okay. First, at any temperature, the chain has anyhow some size. Not that it disappears, it is there. So now I lower the temperature and the size decreases. It decreased up to here. Now it cannot decrease anymore following this function. What happens? It jumps to this branch and then continues going down. So what happens if you lower the temperature is the chain gradually gets smaller. Then you arrive at the temperature corresponding to the minimum. This is the size of the chain. And then if you lower it by a very small amount, the chain collapses here over a considerably smaller size. So here you have a collapse of the chain instead of the gradual crossover. So when you lower the temperature, the chain collapses and its size changes not gradually but immediately to a smaller value, and then it continues getting smaller until it simply gets to fully squeezed, and then you cannot squeeze it anymore. But this you see here by the fact that the function starts to grow very fast. Now, if you start at a globular conformation in the opposite direction, here again, nothing happens, all the changes are gradual. But now you can reach this size, and from this size, pumps, it gets larger immediately. So what you see on this curve is that on one way, this is my curve, this is the red curve. On one way, when you start in a good solvent, you go like this. This is an immediate transition, then you continue like this. But then when you start to heat, you get another way, go like this, and then you continue like this. And these immediate changes. This direct transition is called the collapse of a polymer. And collapses are typical for high molecular weight solvents, but even more typical for for stiff molecules, which I didn't show because we never built a variant of Florey-Huggins for stiff. It's not as simple. So now we are ready. It's enough for today. It's enough with playing with this Florey-Huggins and its variants and relatives. And the take-home messages are that Florey-Huggins approximation allows us for building a reasonable, okay, theory for polymer solutions and polymer blends, which essentially works very nicely for dilute and concentrated solution, and gives the qualitatively good but not exact description for the semi-dilute case, and that the variance of this theory can be used for polymer blends, and the variance of this theory can be also used for describing of what happens with single molecules in solutions, and there interesting things take place. By crossing the theta lines above in the domain of a good solvent, you have swollen chains, you have self-avoiding work chains. Close to the theta lines, the chains are ideal. And below, and this is what we never have seen before, they have globular conformations, which means that they behave essentially like droplets, where all the monomers are together and there is very few solvent inside. Now, what we cannot do with these simple methods is to describe the form of droplets, to describe exactly some of their properties, which are very interesting. For example, if you are indeed looking at long chains in high molecular weight solvent or mixed solvent, maybe that there is the third constituent there, which is again important for biology, but we got some general feeling on what can take place, and we have learned a lot. Okay, other questions?
Professor, I have a question which
Yes.
is not really related to the lecture today. I want to know if you have any idea when our exam would be?
You mean when?
Yeah, when?
The answer is, let me have a look. I know, because I was informed by Mr. Kirstein, who had to inform you, and now let me look into my agenda. And it will be on Wednesday, February 24, just during the lecture hours.
Okay, and are we going to have lectures until a week before? I mean, how many lectures are there?
Wait, this I can discuss with you. Now,
Okay.
look, so we're finished this week. Then we have next week where I can be on Tuesday a little bit later, but not very late because of this defense. And then we have a week starting at February 15 with 2 lectures on February 16, February 17.
Yes.
This, and then we have an exam on February 24. So now we can discuss how we organize this thing. So I know what I will read next week. And what are your suggestions, or what are the questions essentially now?
Actually, I would rather prefer that the last week, I mean February 16 and 17, we don't have any new lectures, so that we can review whatever we had, or we can just get familiar with the type of the exam. I don't know. The closer we are getting to the exam, the more stressful the situation is getting, because I have no idea how the exam would be, and so I don't know if it is possible that we don't have any lectures on the last week, or no.
It's the following. I think that you don't need to sacrifice 2 lectures for this preparation to exam.
Okay.
So what we can do, we can on 17th shortly discuss the make a wrap up, because of course it's useless to do something on Tuesday, February 23, I think.
Yes.
Unfortunately, we'll lose a lecture, and, but I think it's useless to tell you something. It will not stay in your heads. This is what I'm afraid of.
Yes.
Now, what are how the exam will be? The exam consists of variants of homeworks, calculate this, calculate that. Now, the exam, since it is a take-home written exam, which I have to perform online, and I cannot perform it in another way, because some of you are not in Berlin, as far as I know, still.
Yes. Yes.
Yes. So this will contain simple exercises for calculating something, maybe variants of the homework, maybe slightly different variants of the or questions on the same topics, and general questions. For example, if we think about today's lecture, describe conformations of the chain in a good solvent, A, good solvent, B, poor solvent. What are the dependence of the radius on the chain length in this kind of solvents? How does the transition between the conformations take place? So this is an exam question to the second part of today's lecture. This is something like this. And there you have to write it by words. What are the corresponding changes? Something like this.
Okay.
So these are variants of homeworks and the questions on general understanding, or what is the difference between the end-to-end probability density function, end-to-end distance probability density function in an ideal chain and a self-avoiding walk chain? Something like this.
Okay.
Mm-hmm.
So we will have lectures on 16th of February, but not 17. And on 17 we will have a recap.
So we can agree. No, I will definitely have a lecture on. Just a second. I again need to find in my agenda where is the end of February. So we will definitely have a lecture on 16th, and then on 17th we make a wrap up.
Okay.
That's all.
Thank you.
Do we meet on the 23rd, or we don't meet and you learn?
I think we can decide on it on 17th, because
Okay,
I have no idea right now.
Let's decide on the 17th.
Great. Thank you.
Okay, then.
Have a good day.
Have a nice day. And we see each other next week.
Bye.
Bye. Bye. Bye.